speaker. So that I don't see my slides. Good afternoon, everybody. My name is Shiva Shahin, and I'm going to talk about a novel method on the nonlinear refractive index measurement of organic dyes. First, I introduced the self-phase modulation, which is a nonlinear factor in optical fibers. Then I talked about our liquid for optical fiber system. Then I show how we tune the self-phase modulation impact in liquid for optical fibers using different organic dyes. And finally, I introduced our novel method on the measurement of nonlinear refractive index of organic dyes. Self-phase modulation is a third-order nonlinear process that gives rise to an intensity-dependent refractive index. If we write down the wave equation, the simplified version of the wave equation in the fiber, we can see that we have different terms such as the GVD, the growth velocity dispersion. We have the self-phase modulation term, and we also have the loss term. You can see that the self-phase modulation term is dependent upon a nonlinear parameter, which is gamma. Gamma is dependent upon the N2, the nonlinear refractive index of the material that the pulse is propagating through, as well as lambda, which is the wavelength of the pulses. So if for now we assume that we can neglect the impact of the GVD on the pulse propagation, and we solve this equation, we can see that the pulse envelope can be written like this. Looking at the pulse envelope, you can see that gamma changes the phase of the pulse envelope, and that would result in a change in the pulse spectral width of the propagating pulse. So if you look at this equation, you can see that the pulse spectral broadening can be written like this. It is a function of N2. So the larger nonlinear refractive index that we have inside the fiber, the broader the pulse spectral is going to be. However, this impact, you know, is not desirable, and the reason is that so the spectral broadening is a limiting factor in high-power fiber-based laser systems as well as high-bandwidth optical communications. So, slides are not up. So, if you look at this slide, we have shown the pulse spectrum of a 150 femtosecond laser propagating through half diameter of the fiber. So you can see that the output spectrum is massively broadened compared to the input pulse spectrum, and it has also developed some kind of oscillatory behavior. Here you can see the liquid for optical fiber system that we work on. In this picture here, you can see that we have fused silica capillaries with different inner tube diameters, 2, 5, 10 micrometers, and the capillary is tweaked at an angle of 0 degrees. And the standout fiber, which is shown here, you can see that the angle is something between 3 to 10 degrees. And the splicing the two pieces of fiber, you can see that we have a gap between the fibers, and that is for the liquid access. So the liquid that we use for this work has to have some kind of properties. So it has to have a low loss at the wavelength of interest. For this work, we are working in 1550 nanometer. So the solvents that we use shouldn't have any hydroxyl or CH bond in the structure. Also, the liquid that we use has to have large refractive index so that we can have optical waveguiding via the total internal reflection. So the liquid that I chose for this work is carbon tetrachloride. However, we have to mix it with some percentage of carbon disulfide to get the right refractive index. The organic dye that we use for this work is YAG 101A. On the right, you can see the absorbance spectra of different concentrations of this dye. You can see that around 1550 nanometer, the absorption of this dye is very small, so we don't have to worry about the absorption loss of this dye inside the fiber. The interesting thing about this dye is its nonlinear refractive index, which is shown in this table here. We can see that the nonlinear refractive index of this dye is relatively large, and it is negative at 1550 nanometer. So if you look at the cross-section of the liquid core optical fiber in this schematic, you can see that we can basically write the effective nonlinear refractive index into that the pulse is propagating, that the pulse is actually experiencing while propagating through the liquid core optical fiber can be written like this equation here. It is dependent upon the N2 of the silica, the cladding. That is because some parts of the pulse penetrates through the cladding. So it is also dependent on the N2 of the solvent and the N2 of the dye as well, and of course the concentration of the dye. So looking at this equation, you can see that we expect that by changing the concentration of the dye, we should have the ability to change the total effective, basically refractive index that the pulse is experiencing. And so at some specific concentration of the dye, we should also have the ability to totally eliminate the impact of N2. So the experimental setup is shown in here on the left. We can see that we have a mode lock laser with a repetition rate of 50 megahertz and a pulse duration of 150 femtoseconds, which is connected to a liquid core optical fiber, and that is connected to an optical spectrum analyzer with a very good actually resolution. So the input pulse spectrum is shown here. You can see that it is centered around 1553 nanometer. By filling out this liquid core optical fiber with a mixture of CCl4 and CS2, the solvents that I introduced earlier, and measuring the output pulse spectrum, you can see that the spectrum is massively broadened, and that is, as I explained before, due to the N2, the nonlinear refractive index of the solvent itself. So if we replace the solvent in the liquid core optical fiber with the solution of 20 millimole of that dye with the negative N2, the output pulse spectrum is shown here in red. You can see that the pulse spectrum is narrowed down after adding the negative N2 dye to the solution. So to confirm this observation, we actually did some simulation on it. Here you can see that the blue curve here is showing the pulse spectrum of the input pulse. The red curve is showing the output pulse spectrum. So in this slide, the dye concentration is 0, so you can see that the output pulse spectrum is very much broad, and that is due to the N2 of the solvent, of course. If you go to next slide, you can see that by increasing the concentration of this dye, the spectrum is getting narrower until here, using around 13 millimole of the dye concentration, we could totally remove the impact of the surface modulation, and the pulse, the output pulse spectrum is almost the same as the input. So far, I have shown the ability to control and eliminate the impact of surface modulation in liquid core optical fiber systems. Here, I want to introduce a novel method for the characterization of actually different organic dyes. The experimental setup here is the same as what I explained earlier. We have the Motlog laser connecting to a liquid core optical fiber, and the output is connected to an optical spectrum analyzer. So we fill the liquid core optical fiber system with a neat solvent of CCS4 and CS2, and we actually measure the output pulse spectral bits, which is shown in this equation here. Then we replace the solvent with the solution of the dye, some specific concentration of the dye inside the solvent, and we measure the output pulse spectral width again. So having these two measured values and putting the numbers in the pulse spectral broadening equation that I showed earlier, we can see that this subtraction is dependent upon the difference between the N2 of the solution and N2 of the solvent. And we know that the difference between the nonlinear refractive index of the solution and the solvent is dependent upon the N2 of the dye and the concentration of the dye. So here, by two simple measurements of the pulse spectral width, we can see that we can basically extract the number for the N2 of the dye. So we did this measurement on a dye called YZV69, and we basically compared our results to the CIAN results. So you know, CIAN is a very famous method for the measurement of the nonlinear refractive indices of very different materials. So if you compare these two tables, you can see that the results match pretty well. The good point about this introduced method is that it's very much simple, it's accurate, and the liquid core optical fiber that we use for this work is about 0.5 meter, so we have actually a long interaction between the laser pulse and the solution. For that reason, we wouldn't need any high intensity laser beam. And because we don't need any high intensity laser beam, the thermal effects can be ignored, and as well as some higher order nonlinearities. So in summary, I introduced our liquid core optical fiber system, which gives us the ability to investigate the nonlinear properties of different organic dyes in basically different solutions. We showed the ability to tune and to cancel out the surface modulation that is caused by the solvent inside the hollow core fibers and by the cladding of the fiber itself. And we actually introduced a novel technique to measure and to basically characterize the nonlinear refractive index of different organic chromophores in a solution. With that, I complete my talk. This work was supported in part by COMAS and by CIAN ERC. Thanks for your attention. Is there any question?
So if you have questions, you can turn on your microphone and ask, or you could type your questions into the chat line. I'll start with one. Actually, how do you get these materials into your fiber?
So to answer that, I go back here on this slide. So the two pieces of the fiber that are spliced, you can see that there is a gap between the two fibers. So basically, this splice that you see here is here, like underneath the vial. So we fill the vial with the liquid of interest, and the liquid goes through the capillary fiber through the capillary action. Does that answer?
Yeah, so you don't actually have to apply pressure or anything. It's just small enough that it sucks it right in.
Could you repeat
So there's
that?
no pressure, you aren't having to squeeze the liquids in there.
No. So that goes through the fiber just with the capillary
Okay,
action.
thank you. Looks like you have a few more questions
So
in the
there's
chat
no
line
need
here.
to have any questions. So there is one question, is there any limits to the practical ranges of N2 this technique can measure? I would say no, or probably not something that I have in mind right now. So now there are some limitations. One is that the chromophores that we choose, they have to have a low loss at the wavelengths of interest. We have to get the output so that we can measure the output spectral width. And so the solvents of that chromophore that we use, that solvent has to also have a low loss at the wavelength, and it, as I said before, it has to have a right refractive index. Except that, I don't see any limit. You can see in this equation. So, except loss, I don't see any limit for the ranges of N2.
Okay, and there was one before him. Pierre had asked, what is the broader impact of this system?
So, I'm not sure if you're asking about the method on the characterization of organic dyes, or just the ability to tune or cancel out the SDM impact. So if you're asking about the ability to tune and cancel out the surface modulation, so we know that surface modulation is a limiting factor. So by surface modulation, we get crosstalk between different channels. So with this technique, we can basically remove the broadening of the pulse. Okay, I see you are asking about being able to broaden the spectrum. So the goal here is basically to remove the broadening impact, or at least to have a control over the broadening impacts of the surface modulation. Does that answer your question? Okay. Any more questions?
Okay, doesn't look like there's any more questions, but thank you, Shiva, for speaking to us today.